In this lesson, we'll continue our discussion of chemistry by taking a look at chemical bonding. So when atoms interact with one another to form new substances, a bond needs to be established. And that's what we're going to focus on in this lesson here, chemical bonds. They're going to form both molecules and compounds. Let's take a look at the difference. A molecule is a chemical, right, chemical structure consisting of atoms held together by the sharing of electrons. These are usually strong bonds, all right? So chemicals consisting of atoms held together by the sharing of electrons. Opposed to a compound, this is a chemical, right, a chemical substance made up of atoms of two or more different elements in a fixed proportion regardless if electrons are being shared. So we're going to see there are some bonds that are formed where there is no sharing of electrons. Most people kind of use these two words interchangeably. I wouldn't get too hung up on it. So in order to understand how bonding takes place, we want to be able to write kind of like a chemistry way of writing things. So I want to go over something called chemical notations, right? This is used to describe the chemical compounds and the chemical reactions in the body, right? We can use this chemical notation to describe atoms, molecules, various chemical reactions, and then something known as ions. So let's take a look here. Let's just say we have some atoms, right? We want to know now, how do we write that out? What's the chemistry way of writing atoms out? So let's just say, for instance, over here, we have just one single hydrogen atom, okay? If there's just one single hydrogen atom, right, and this is the visual representation, we would just write it as an H. We don't have to put one H, H1. We don't have to do anything like that. Just an H by itself. We know that H is this chemical symbol for hydrogen. Just H by itself tells us it's one. But let's say we have two hydrogen atoms. Notice they're not bonded together. They're just two individual hydrogen atoms. The way we'd write that is 2H. So that tells us we have two hydrogens, right? This would be, again, on this side is the chemical notation. This is the chemistry way of writing things. Same thing with oxygen. One oxygen, we would just put O. Two oxygens, 2O, right? Four oxygens, 4O, right? So that's how we write down atoms. How about molecules? Okay, let's say we have now two hydrogens, but notice, guys, they are bonded together. The two hydrogens are together, they're not individual. In this case we would write it as H2. So when we write the 2 afterwards as a subscript, that now tells us these two hydrogens are bonded together. Oxygen, oxygen, right? They're bonded together. O2, right? Oxygen, and then a 2 after it. Okay, here's a water molecule, H2O, right? Two hydrogens bonded to oxygen. So we would write that H2, 2, and that's bonded to oxygen as an O. Okay, so this is how we would indicate a molecule. You'll get used to it as you see them more and more. Reactions. So we're gonna in a subsequent lesson we're gonna go into the different types of reactions. So I just want to introduce to you how we usually write them out. Let's just say we're gonna make water. Right, here's H2O. We want to make it. So on this side are the atoms that are going into the chemical reaction. We call them the reactants, and by convention we usually draw them on the left. It does not have to be that way, however. By convention, we do that. So here we have the reactants. They're all going to go into the chemical reaction. Then we indicate an arrow, and then what's formed, right, the new chemical is known as a product. Okay, so instead of drawing this out, we want to be able to write this in, again, chemical language, chemical notation. So we have two H's here. Again, why is it not H2? Is because they're not bonded together. Plus an oxygen yields, right? This is actually the yield symbol, creates H2O. But this time now we have everything bonded together, so we're going to write H2 as a subscript O. The last thing on this slide, here they're showing you a balanced equation versus an unbalanced equation. Basically what that means is the number of atoms on this side equals the number of atoms on this side. All right, so this would be a correct way of notating it because it's balanced. Here we have two hydrogens. On this side we have two hydrogens. Here we have one oxygen. On this side we have one oxygen. All right, if you look at the unbalanced equation, we have two hydrogens here, but two oxygens, but only one oxygen. So this would be an unbalanced equation. This two over here kind of threw things off. Okay, so again, reactants are typically written on the left. The product, what is formed, is written on the right. There's the yield arrow. Okay, so that's the how we notate a reaction. Okay, let's take a look at how we notate an ion. So just real quick, as far as what an ion is an atom that either gains or loses an electron to become stable. So you'll see things like sodium, potassium, calcium, chloride. Those are some of the ones that we use a lot in anatomy and physiology. These are elements that in order for them to become stable, they would like to lose or gain electrons. So if you have your periodic table out for a moment, take a look at sodium. So if you see sodium, sodium has an atomic number of 11. So that tells us there are 11 protons. Right? We're not seeing them on this diagram here, but it also tells us we have 11 electrons. So if you remember from our previous lesson, where is the first two electrons go? It's going to go in the first shell. Here's one here above my cursor, and then here's one here above my cursor. That's in the first shell, so that's 2. That means 9 are left over. So we're going to put 8 in the second shell. 1, 2, 3, 4, 5, 6, 7, 8. It can't take any more. That means the extra electron is going to go in the third shell. But here's the deal. In order for an atom to be stable, it prefers to have its outermost shell full or have at least 8. Well, how many are in the outermost shell is just 1. So sodium can do two things. It can gain 7 electrons from somewhere, or it can give 1 up. Take a guess. What do you think is easier, to gain 7 or give up 1? It turns out sodium prefers to give up that electron. It'll give off that electron. Now it has how many electrons in its outermost shell? 1, 2, 3, 4, 5, 6, 7, 8. And there's something known as the excuse me, the octet rule, or the rule of eights. In order for an atom to be stable, the outermost shell must be full or have 8 electrons. So now sodium has 8 electrons in its outermost shell. It is stable, but what did we lose? An electron. If you remember from our previous lesson, what is the charge of an electron? It is negative. So by losing one negative, we're positive by 1. Why is that? We had 11 protons, but now we have 10 electrons. So we have to indicate sodium with a plus sign. And if you notice here, guys, sodium is always written with a plus. This plus indicates that we have one more proton than electrons. And the reason for that is the sodium atom has given up 1 electron in order to become stable. I have this for you in a minute. Don't write it down now, but we call a positively charged ion a cation, C-A-T-I-O-N. All right, let's see if we have that up over here. Yeah, right here. This word here, cation, right there. Okay, I had this on another slide. I just want to throw it out there. Calcium, same thing. We're not going to draw it out now, but calcium, in order for it to become stable, guess how many electrons it lost? It lost 2. So that means it has two more protons than electrons, and that's why it's on a positive charge. So typically you're going to see calcium written as uh, a plus 2. Chloride, watch this. Chloride is missing an electron in its outermost shell. It only has 7. So in order for it to be stable, this could either lose 7 electrons or gain 1 electron. Again, I would ask you, what's easier, lose 7 of something or gain 1? And it's probably going to be easy for it to gain 1. Guess where it probably could gain it from? Who just gave 1 off over here was sodium. Right? So when sodium gives 1 off, chloride could pick that up. This here is a negatively charged ion, and this we call an anion right there. This is known as an anion. Again, I had this on another slide. So again, what is an ion? An ion is an atom that either gains or loses an electron in order to become stable. So that outer shell has is full, or it has 8 electrons in it. Okay, so it's important to notate, right, chemical notation, the ions with a plus or a minus. Okay, sometimes you even hear these ions referred to as electrolytes. Okay, so let's take a look now at the various bonds that we're going to take a look at. We're going to take a look at 3 bonds. We're going to take a look at ionic bonds, covalent bonds, and then something known as hydrogen bonding. This is actually an interaction between two molecules that have been formed already. These hydrogen bonds don't make a new compound or new molecule. They're just going to be an interaction between two molecules that have already been formed. So let's start with ionic bonds. So look at the name for a minute. Just think about this. Ionic bonds, probably, if you think about it, are going to involve ions. Again, I'm going to go back a slide. Probably going to involve these kinds of things right here: sodium, chloride, calcium, potassium. Those are, again, the main ones we use in the body. So let's take a look at this. All right, so we said before that an ion is an atom with an electrical charge. Again, we're doing ionic bonds. One atom, the electron donor, loses 1 or more electrons. So the examples we just gave on the previous slide was sodium and calcium. Right? Sodium gives up 1 electron and becomes positively charged. Calcium, we saw, gave up 2. I didn't do potassium. I didn't talk about that. Potassium is like sodium. It gives up 1 in order to become stable. Excuse me. So this is going to be positively charged. These are going to be positively charged cations. Another atom, an electron acceptor, gains those same electrons to become an anion. Again, an anion is a negatively charged ion. A cation right here is a positively charged ion. Right? And how can you remember that? The T looks like a positive sign, doesn't it? And anion, N for negative. All right, that's how I always remember it when I was a student. The T has a positive sign in it, right? The T is like a positive sign, like that. The anion N has a negative. So chloride would be a negative. This was an example of an atom that gained an electron to become stable. So here's the deal. If we were to take sodium and then put it in the proximity of chloride, sodium would give up the electron. Who would pick it up? Chloride. And what's the deal? A positive is going to be attracted to a negative, right? The rule is always opposites attract. So now we're going to get this bonding because the positive is attracted to the negative. And that's this, highlight right here. Ionic bonds are attractions. That's the key word, between cations and anions, between what's positive and negative. If you always remember, opposites attract. So we're only going to see ionic bonds with ions. Positives will be attracted to negative. So let's take a look at sodium chloride. We'll go through this nice and easy. Up top is a sodium. How do I know that? Na. Okay. If you take a look at its atomic number, if you have your periodic table out, its atomic number is 11. Okay, so that tells us how many electrons? 11. Ready? 1, 2 are always in the first shell. It can't hold any more. Then 3, 4, 5, 6, 7, 8, 9, 10, right? So that's plus 8, right? So that's 8 in the second shell. The second shell can't handle any more, so the 11th one is in the third shell. So we said previously, in order for sodium to be stable, it can either gain 7 or lose 1. And we saw on the previous slide, it's going to lose 1. Chlorine, right? Chloride, watch this, has 1, 2 electrons in the first shell. Then 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell. So that's 2 and 8 is 10. And then how many electrons in the third shell? 1, 2, 3, 4, 5, 6, 7. All right, so it had 17 electrons, but the outermost shell has to be either full or contain 8. Right, it only has 7. So it can either lose all 7 or gain 1. And we said earlier, who can give him 1 is the sodium. So now, when we gave up these electrons from sodium to chloride, sodium ended up having a positive charge. The chloride accepted that electron. It now became more negative. It has 1 extra electron than protons, so it's more negative. So what's the rule? Opposites attract. The positive of the sodium is pulled towards the negative of the chloride, and now these two are going to be in close proximity, and this is known now as sodium chloride. All right, this is plain old table salt. Most structures in our body that are hard structures, like bones and teeth, and salts and that type of thing, they're going to be ionic bonds. All right, so you can see here is a big salt crystal where you have the chlorides in green, and the purplish is going to be the sodiums bonded together. And here's an actual sodium chloride, excuse me, crystal. Okay, so again, the main rule with ionic bonding is that we're going to get ions. One's going to be positive, one's going to be negative. The positive charge of one ion is going to be attracted to the negative charge of the other ion. Now, the second type of bonding is known as a covalent bond. Right? This is going to be for elements or atoms that don't become ions, right? Not every atom can gain or lose electrons, because otherwise all we would have is ionic bonds. So that's my first statement here, my first sentence. Not all atoms gain or lose electrons to become stable. Some atoms can complete the valence shell, right, to get that number of 8 by sharing electrons with other atoms. That's the key with covalent. Highlight right here. Sharing. Covalent bonds is the sharing of electrons. Okay, and we're going to see that covalent bonds are nice, strong bonds, and we have a couple different types. If there's just the sharing of one pair of electrons, like this right here, one pair, we call that a single covalent bond, and we usually draw it as a little line. If there's a sharing of two pair of electron, we call that a double covalent bond. We'll see that as 2 lines. These we're going to see in anatomy and physiology the next couple semesters, single and doubles. Triple we're not going to really see. A triple bond is the sharing of 3 pair of electrons. Okay, so again, covalent bonds are strong bonds. They are the result of a sharing of electrons. Let's take a look. So let's do hydrogen gas for a second. Hydrogen gas has the formula H2. So we're basically going to be bonding 2 hydrogens together. So if you take a look at your periodic table, way up in the left hand corner, you're going to see hydrogen has the atomic number of 1. That means it has 1 proton and it has 1 electron. Right? It also has atomic mass of 1, so that means it has no neutrons, but we don't really care about the neutrons. So watch this, guys. Let's say this hydrogen on the left here is nucleus, and then here's like the first shell. So let's just say the orange electron belongs to the hydrogen on the left, and then this hydrogen here has the yellow electron. So in order for them to be stable, their outermost shell must be full. The outermost shell is the first shell. So think about this for a minute. How many electrons can the first shell hold? Only two. So here's what happens. This orange electron from the left hydrogen and this yellow electron from the right hydrogen, these two electrons are going to be shared between both hydrogens. Now, this one here on the left, this hydrogen on the left, has 1, 2 electrons. It's stable. This hydrogen on the right is using 1, 2 electrons. It's stable. Okay, since we're sharing one pair of electrons, we draw that as a single line. All right, so we draw it H, line, H. That line tells us right here, it's a single covalent bond. It's the sharing of one pair of electrons. All right, so we're going to see a lot of those in AMP1. How about oxygen? So if you take a look at oxygen, oxygen on the left has 2 electrons in its first shell. That's 2. And then 1, 2, 3, 4, 5, 6 electrons in its outermost shell, the second shell. So since it only has 6 electrons, it needs 2 to become stable. Because what's the rule? We need to have the outermost shell full, or at least have 8. So if we can get 2 more electrons, we'll have 8. Okay, but it doesn't become an ion. Oxygen also would rather share electrons. So if we bring another oxygen up against it, this is going to be oxygen gas, right? O2. Let's do the oxygen on the left. Let's only worry about the valence shell. It has 6 electrons, but it's going to need 8. So it has 1. Let's do the yellows. 1, 2, a third yellow here, a fourth yellow, a fifth yellow, a sixth yellow. But now notice it can share 1, 2 oranges over here. So now the outermost shell has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen on the left is happy. It has 8 electrons in its outermost shell. And just as a mirror image, this one on the right is doing the same thing, right? 1, 2, 3, 4, 5, 6, 7, 8. So here, guys, we're sharing not just 2 electrons, but 2 pair. When we share 2 pair of electrons, we draw that as a double bond. All right, so oxygen is written like this: O double bond O. Here's an example of carbon dioxide, right? This is what we breathe out. This stuff up here we breathe in, this stuff we breathe out. So if you remember, carbon has an atomic number of 6, or if you have your periodic table out, carbon has a atomic number of 6. That tells us it has 6 protons. It also tells us it has 6 electrons. So watch this. The first 2 electrons are in the first shell. That means there are 4 electrons in its outermost shell. Let's check. They're gray, right? So 1, 2, I'm sorry, 1, 2, and then 3, 4. So there's 4 in the outermost shell plus 2 in the inner shell gives us a total 6. Since there are 4 electrons in the outermost shell, carbon wants to share 4 electrons elsewhere. And watch what it's going to do. It's going to share 2 with an oxygen on the left, because remember, oxygen only needed to share 2. We saw that here. And then it's going to share another 2 with this oxygen on the right. So carbon dioxide, look at this, is a carbon with a double bond to the left, sharing of 4 electrons. 1, 2, 3, 4. And then a double bond to the right side. 1, 2, 3, 4. Now, this is just an example of a triple bond. We're not going to do any triple bonds in our class this semester after today or after this lesson. This is nitrogen. So let's take a look at nitrogen. How many electrons are in its outermost shell? 1, 2. We're doing the green, right? 1, 2, 3, 4, 5. and then it had 2 on the inner shell. So if you take a look at nitrogen, nitrogen had an atomic number of 7. Okay, so 2 electrons in the innermost shell, but 5 in the outermost shell. 1, 2, 3, 4, 5. So since it has 5 in its outermost shell, how many electrons does it need to share to become stable? Right? The magic number is always 8. So that means it needs to share 3. So you'll notice, guys, each nitrogen here is sharing 3 from the other nitrogen. Let's start with this guy here. 1, 2, 3, 4, 5, 6, 7, 8. So this one here on the left is happy, and then it's a mirror image on this side. 1, 2, 3, 4, 5, 6, 7, and 8. Right, so this would be an example of the sharing of 3 pair of electrons. So we draw that as a triple bond. So like I said, in this course here in AMP2, you really won't be doing too many things with triple bonds, more like single bonds and double bonds. Okay, and then I'll let you look at this one on your own. This is an example of nitric oxide, NO, where we have a nitrogen and oxygen. And see if you can figure that one out. I'll let you do that one on your own. All right, so this is all what we call sharing of electrons. So that is a covalent bond. Now there's 2 types of covalent bonds. What we just looked at, those, what do we do? 1, 2, 3. These 4 examples that we just did, there was an equal sharing of the electrons because both molecules, I'm sorry, both atoms on either side of the bond were pretty much the same. It was pretty much like a mirror image. If I cut down the middle here, the left is a mirror image of the right. If I cut down the middle here, the left is a mirror image on the right. Even if I cut straight through carbon here, the left is a mirror image on the right. And same thing with nitrogen. So the electrons are shared equally. So non-polar covalent bonds are the sharing of electrons, but it's an equal sharing of electrons, and there's an equal pull on each side. But that is not the case always. Sometimes one atom has a stronger attraction and pulls the electrons closer to it, further away from the other atoms in the molecule. And what that does is it causes the entire molecule to have a charge. The entire molecule will be positive on one side and negative on the other side. And I'm going to go back to these notes in a minute. Let's take a look at water. This is a great example of what I'm talking about. So watch this. This big orange thing here is an oxygen. So again, look at your periodic table for a minute and think about what's the atomic number and then how many electrons, right? And you should come up with 1, 2, 3, 4, 5, 6, 7, 8. Right? So the atomic number of oxygen was 8. That meant it had 8 protons plus 8 electrons. The first 2 electrons are in the first shell. That's all it can hold. That means the other 6 are in the outermost shell. And we actually did that before. So how many electrons does oxygen need to share? 2. So watch this. Hydrogen we saw, again, go to the periodic table. Hydrogen had 1 electron in its outermost shell. How do I know that? It had the atomic number of 1. 1 proton, 1 electron. Here's another hydrogen, 1 proton, 1 electron. So are these stable? The answer is no, because hydrogen needs how many in its outermost shell? It can hold 2. This one can hold 2. So good news. The oxygen will share this electron here to have a 7th electron and share this electron here to have an 8th electron. Now oxygen is satisfied. Each hydrogen will be satisfied because they're going to share 1 electron from oxygen, and this is what the bond will look like. It will come over here. It will look like, kind of looks like Mickey Mouse ears, so to speak. Oxygen is a bent molecule. It's actually going to be bent. So now we have H2O. And again, if you count the electrons, this hydrogen right here has 2 electrons. It's happy. This hydrogen has 2 electrons, and the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Since we're sharing a pair of electrons here, that's a single line when we draw it. And we're sharing a pair of electrons here, that's a single line when we draw it. Right, so we usually write H2O as a O with one line coming off with a hydrogen and then one line coming off with a hydrogen. But here's the deal. Oxygen has a stronger affinity for electrons. It has like a natural attraction, a pull of the electrons. So even though we're going to be sharing the electrons here and here, the electrons tend to spend more time over here on the oxygen side and less time over on the hydrogen side. What's the charge of electrons? They are negative. Since the electrons spend more time over here, this side of the water molecule is going to be negative, and we usually write that, you don't have to know the symbol, but this is called a delta. But see that negative sign? That tells us this side of the water is negative, and in comparison, the hydrogen side is going to be delta positive. All right, so water is one side of the molecule is more negative, the other side over here is more positive. Why is that? Oxygen has a natural, stronger attraction of electrons. It kind of pulls the electrons closer to it. They're still sharing, it is just unequal sharing, and that's going to form what we call a polar molecule. A polar molecule is something that has two charges on it, a positive charge and a negative charge. Right? If you think about your battery in your car, if you have a car, if you were to open up the hood of your car and look into your hood, you would see the battery. And then from the battery, there's two things sticking up that the wires are on. Or when you do jumping a car, you put the jumper cables on those two things. Those are called poles. One is a positive pole, one is a negative pole. All right, so a battery is polar. So is water. It has a negative side over here and a positive side. Why is this important? By understanding that water is polar, it'll help us in a subsequent lesson understand how water interacts with other substances and allows things to dissolve in it, while some things can dissolve in water, but not everything. For example, if you took salt and you put it in water, the salt will dissolve in water. But if you took oil and put it in water, it would not dissolve, right? You would have like an oil droplet in the water. And that's because oil is nonpolar, and nonpolar things don't mix with polar things. We're going to get into that. For today, I just want you to understand that not always is the sharing of electrons equal, right? Here we have sharing of electrons, sharing of electrons. But the electrons tend to stay more on this side. They do come over here, but less. So as a result, the oxygen side of water is negative, the hydrogen side is more positive. Okay, the last thing we want to look at in this lesson as far as bonding is hydrogen bonds. So it's important to know hydrogen bonds, guys, do not make new atoms. I'm sorry, I apologize. Hydrogen bonds do not make new molecules or compounds. It is really just an attraction between two molecules that have already been formed. All right, so these are weak bonds between adjacent molecules. That first sentence is so important, right? These are weak bonds between adjacent molecules. These are also based on electrical attractions. So before I read these notes, let's go to water for a minute. Would everybody agree, right, in their mind? Here's one water molecule here, H2O. Here's another water molecule, H2O, right? Kind of looks like Mickey Mouse. H2O. And we also said from our previous slides, the hydrogen side is positive, the oxygen side is negative. So watch this, guys. This water molecule here is close to this water molecule here. What's the rule? Opposites attract, exactly. So the positive charge of the hydrogen side is going to have a weak attraction to the negative side of this water molecule, the oxygen side, right? Right? Watch this, positive, negative. So this bond that forms is what we call a hydrogen bond. It's between this hydrogen here and this oxygen. Most of the time, hydrogen bonds are between the hydrogen of one molecule and an oxygen on another molecule, but it could be nitrogen also. Right? But for water, we're going to see it's between the positive side where hydrogen is and the negative side where oxygen is. Again, what do we say? It's an electrical attraction. Right? Opposites attract. So this water molecule is now attached to this water molecule by a hydrogen bond, the positive side of this hydrogen and the negative side of this oxygen, and so on and so forth. So all our water molecules now are held together. And again, this is going to be responsible for some of the properties of water. For instance, if you took a shower this morning, right, when you got out of the shower, you weren't just completely dry. You had a bunch of water droplets on your skin. You had to take a towel to dry yourself off, right? The fact that hydrogen bonds are holding these water molecules together allows it to actually stick to us. That's called surface tension. So this actually helps to even form the water droplet itself. Okay, so hydrogen bonds again are weak bonds between adjacent molecules. They don't form molecules. They're taking molecules that are already held together, and now the electrical attraction holds the molecules together. Right? It involves the attraction between uh, a slight positive charge and a slight negative charge. Right? The slight positive charge comes from the hydrogen, and the negative charge in this case of the water comes from the oxygen. And I'm just repeating it again. Hydrogen bonds do not form molecules. Okay. And this is what I said before, hydrogen bonds between water molecules causes surface tension. This is what causes water to stick to a surface and form like a droplet. Okay, so that's a pretty good picture. We're going to get into this more and more. We're going to see hydrogen bonds hold strands of DNA together. We see hydrogen bonds hold proteins into a specific shape. Right, today's the first time that we're seeing it holding water molecules together. Okay, so the last thing that we want to go over, when we have new compounds and molecules formed, we have three states of matter. Okay, three states of matter. We can have solids, right? Kind of hard things. These are things that have constant volume and constant shape, right? Your desk that you're sitting at maybe today is the same as what it looked like yesterday, and it's going to be the same as it looks like tomorrow because it is solid. Liquid has a constant volume, but it can change its shape. Right? You think about if you pour a glass of water, has the shape of the glass, but then if you pour that water into a bottle, it's going to take on the shape of that bottle, right? So it has the ability to change shape. That becomes important when you study blood next semester. And then gases, these have the ability to change their volume and their shape. We can compress gases, we can allow gases to expand, right? They can change their shape based on the container that they're in. That becomes important in AMP2 when you look at the respiratory system. Okay, so that concludes this lesson on chemical bonding. In our next lesson, we'll take a look at various types of chemical reactions that take place.